Hello, I'm Joe Bakos, and I'm welcoming you to this week's edition of the Taurus Report, where we are going to take a look at why, if I think that general relativity is mistaken, then why was it so convincing, and why do most cosmologists, most astrophysicists still strongly believe in it? Recall that last week we were talking about special relativity. So, special relativity, we discussed how Einstein was able, with special relativity, to explain the results of the Michelson-Morley experiment. In other words, why was it that when doing the experiment, the light coming from those two different directions that we discussed arrived at the same time? So, why did that happen? Now, Einstein explained that all of space, for a person traveling at velocity, all of space in that direction becomes compressed. And because it becomes compressed, the light that went to the forward mirror and back arrived at the same time as the light going to a transverse mirror and back. And recall that I made the claim, and we'll get to justifying this claim later, that I'm siding with Lorentz, who initially, to explain that, Lorentz did not say that all of space was contracting in that direction, but only the apparatus that's moving was contracted in that direction. And he was trying to base that claim on physical mechanism related to electromagnetism, which I think is correct. So, but Einstein was able to explain the Michelson-Morley result, but not only that, he made several other predictions, and this is where we get into general relativity. And because Lorentz's vision was not able to deal with these other predictions, eventually everybody sort of not sort of. They adopted Einstein's view because it was able to explain more. So, what are the other things that Einstein explained using general relativity? So, general relativity relates to the fact that we have some similar things happening when you are traveling at relativistic velocity and when you're descending into a gravity well. And it seems strange that these things should happen in both these contexts. So, what are these things? What happens in both those environments? So, at relativistic speed, and when I use the word relativistic in this sense, all I mean is really fast. Relativistic means that you're traveling at some appreciable fraction of the speed of light, which is 3 times 10 to the 8th meters per second. Really fast, okay? It's speeds that we're just not used to dealing with in our day-to-day lives. But if you start traveling at some appreciable fraction of the speed of light, then you start seeing some of these effects. So when something's traveling that fast, we call it a relativistic velocity. So at relativistic velocities, there is some compression that's going on, length contraction. I say it's the length of that object that's traveling. Einstein says that it's all of space for someone traveling at that relativistic velocity. And there is also time dilation, which Lorentz did not have a good explanation for. That was not part of the Michelson-Morley explanation. That came later. That is another prediction that Einstein was able to make, which Lorentz could not deal with, and so this is why Einstein's vision was adopted. So there's some kind of length contraction, and also time slows down. The faster you travel, the more time slows down for you. Now, the same thing, and this is what's interesting, those same things happen if you're in a gravity well. By gravity well, I mean you're getting near the surface of some massive object, like a star or something. Some massive object, you're getting near to that. So let's see, all three of those things happen. You get length contraction, you get time dilation, time slows down, and you also get the object becoming more massive. And most people who are not familiar with these things would say, wait a minute, so something traveling at relativistic velocity just suddenly becomes like more massive? And yes, it does. So all three of those things happen in those two environments. And a natural question is, how can that possibly be? How can you have those three things happening in those two different environments? So how was Einstein able to explain all this? He did it by using non-Euclidean geometry, wherein he treated time as if, well, sort of like it's a fourth dimension of space. And he said that both gravity and traveling at relativistic velocity warps or deforms this space-time continuum. So the famous saying that everybody quotes is that matter tells space how to curve, and space tells matter how to move. So let us take a look at each of the various predictions that Einstein made. So first one, precession of Mercury. Astronomers noticed that Mercury did not follow a perfect ellipse around the sun, which is what Newtonian theory, gravity according to Newton, that's what is predicted. Mercury should be orbiting in a perfect ellipse. Well, according to Einstein, because the sun is so massive and Mercury's in a region of space that's very close to the sun, the space is warped by the sun, and so the path of Mercury as it goes around the sun does not form a perfect ellipse. Instead, it makes sort of a kind of a spiral pattern. If you've ever used that old children's pastime, the spirograph, it makes kind of a spirograph pattern. And one thing I'd like to note about this, because CGC, cyclic gravity and cosmology, models which I've done, and again I will include the link in the comments for this video, show also this sort of precession, this sort of spirograph pattern. And I want to note something about this prediction of Einstein's. In, I'll call it extreme situations, where you have a really massive object, or an object's orbiting very close to a massive object, or in the case of galactic rotation rates, we have the opposite extreme. It's also an extreme circumstance, but it's the opposite extreme, where you've got a star that's orbiting very far from the center of the galaxy. So we've got extreme distances. So in these extreme cases is where you'd expect to see variation from standard gravity. And if you have standard variation, then any gravitational law that is not, where gravity is not proportional to the distance squared, will not give a perfect ellipse. In other words, you're going to have some sort of imperfection. And so in some ways, Einstein's prediction would have been true no matter what gravitational force he came up with, as far as predicting some sort of precession. Okay, if you differ from a simple proportional to distance squared law, then you're going to get a sort of a rosette pattern, sort of as comets behave orbiting the sun. Any sort of law that isn't standard Newtonian is going to give you some sort of precession like this. And so in the simulations which I show, and again I will link those in the comments, it shows that CGC also predicts this. Now the other thing that Einstein predicted with his equations relating mass to space is it predicts that an object traveling at relativistic velocities becomes more massive. Now, some theorists sort of criticize me for saying that, because I shouldn't say, strictly speaking, becomes more massive. It should be greater than expected momentum, a relativistic momentum. But for a layperson, if we say it just becomes heavier, that's kind of what's happening in lay terminology, and I'm going to stick to that. I'm just going to say an object at relativistic velocity becomes more massive, even though that isn't strictly speaking correct, because it has the same quantity of matter, like the same number of atoms and all of that, but they just have more energy than expected. And energy is mass. Okay, so anyways, that's another prediction. So as you go into a gravity well, or you travel at relativistic velocity, you become more massive, right? If you go to the surface of Jupiter, you'd weigh a lot more than you weigh on the Earth. Also, if you travel at relativistic velocity, the amount of mass that someone at rest would calculate for you would be different than what you'd be expecting. So general relativity predicted this. And also general relativity predicted the compression of space, both in a gravity well and also at relativistic velocities. Now, this led to one of the most famous predictions of Einstein's that was borne out was the fact that light going around the sun would be bent in its path more than predicted by Newtonian physics. And this turned out to be true. Now, since under electromagnetic theory, gravity does not act on light, then it doesn't really make sense that the path would be bent that much. And Einstein explained it by saying that space is bent, and so around a gravity source like the sun, space is bent, and so as the light goes by, it follows this bent path. So let's see, did I cover all three of those things? Increase of mass, deformation of space, I call it deformation, and time dilation. Oh yes, that's the last one. It is found that in a gravity well, time slows down for an object in a gravity well. And so all three of these things happen in similar ways in those two very different environments. In a gravity well and at relativistic velocity, all three of those things happen. And Einstein, with his equations, was able to predict all that. And so then it begs the question, if it explains all that, why would we consider something else? Why should we take a look at CGC? And also, if we're going to take a look at CGC must also explain those same things. Otherwise it wouldn't be worth considering. It must also explain what's going on, but then be able to explain other things that general relativity does not explain. And so we'll take a look now at CGC, how CGC explains those three things in those two different environments. In the previous segment, I mentioned that I've shared some simulations using a gravitational force law, simulating the formation of a solar system with planets using CGC. And I am going to link this video in the comments to this video. So you can look at this simulation and you see these spirograph patterns that develop, showing that CGC is consistent with something like the precession of Mercury. Now, as a little bit of housekeeping once again, I just want to share with you how to get to my website. So if you open a browser window and you just type in Torus report, all as one word, .com, and hit enter, then you'll come to my website. And there's various links here. And the link to my paper, CGC, 23-page paper on cyclic gravity and cosmology, wherein I explain all this in much more detail. And the part that I'm interested in right now is taking a look at these things we've just been discussing about the predictions of general relativity. And how does CGC explain these things? Okay, how does CGC explain these things? And I'm going to skip ahead a little bit to one portion of CGC, which is an assumption that I make about cold neutrinos. So let us talk about that for a second here. And why do we want to talk about cold neutrinos? So cold neutrinos are going to answer two questions, two aspects of these things. One is about the deflection of light around a gravity source. It is my contention that gravitational sources attract neutrinos, and I call them cold, meaning that they're not moving very fast. Now, the difficulty with neutrinos is they're almost impossible to detect, and the only neutrinos that we can detect in our detectors are hot neutrinos or fast neutrinos, and those are the only ones that show up. They have to be of sufficiently high energy for us to detect them. In fact, we're surrounded by a very dense sea of neutrinos, but because neutrinos are so weakly interactive, they are barely detectable. And as I said, the only ones we can detect are hot ones going very fast. So I'm assuming that any gravitational source attracts a dense gradient of cold neutrinos, and it is this dense gradient of cold neutrinos that deflects light around a gravity source. So in my paper, I depict it with this illustration here. So here's the surface of the sun. And then I assume that the neutrinos are in a concentration gradient of increasing density. And so the light is bent around a gravity source just by simple refraction. This is a well-known property of light when it goes through some kind of gradient like this. And so that is one aspect of cold neutrinos, explaining one aspect of these things that Einstein explained. What else? The other property of neutrinos that I claim that they have is that they inhibit other quantum processes. So if quantum processes are inhibited, that's just a fancy way of saying that time slows down. It's sort of like if you take bacteria, you put them in the fridge, because molecular motion is inhibited when things are cold. For a living organism like a bacteria, all of the motions of the molecules within the bacteria slow down, and so everything slows down. And I am claiming that high concentrations of neutrinos around a gravity source inhibit quantum processes, and this causes time to slow down in a gravity well. Now, also, that would explain why time also slows down at relativistic velocities. The reason why time would slow down at relativistic velocities is that as you're traveling through space faster and faster and faster, you're going to encounter more neutrinos than you would if you were standing still. And because you encounter more neutrinos, time slows down for you. And so I'm claiming that these are sort of objective, physical things that are happening. These are physical phenomena with a physical mechanism that time dilation is happening because of cold neutrinos. Neutrino encounters, and it is also explaining the deflection of light. Now, what about increase of mass? So, increase of mass in a gravity source, because CGC claims that gravity is a relic of the electromagnetic force, the more matter you have, the more atoms you have, then you have a greater quantity of these forces. And so that aspect of things people sort of intuitively understand that, if you have a more massive object, like on the surface of the Earth, I weigh more than if I was on the moon, because the moon's gravity is less. And so that part of increase of mass, I think everybody gets. And in CGC and in general relativity, that part of things is the same. Okay, both CGC and general relativity come up with the same sort of explanation for why there's increase of mass around a massive object, right? Gravity is stronger around a massive object. But what about a relativistic velocity? Now again, with CGC, it comes down to a physical mechanism. Because gravity is a relic of the electromagnetic force, then if you move at velocity, you have a stronger magnetic force. And so it makes perfect sense that moving at velocity causes an object to appear more massive. And if you're moving along with that object, it doesn't appear more massive, because that is the nature of the magnetic force. Right? From last episode, we were discussing that, and I explained how if you're moving along with an electric charge, then you will not detect a magnetic force from that electric charge, whereas somebody standing still as an electric charge passes him, he will detect a magnetic force caused by that electric charge. And so it makes perfect sense that this physical mechanism also explains increase of mass at relativistic velocities. So CGC is able to explain all these things without treating time as if it's another dimension of space, okay? And also without deforming space. Like space is never stretched or contracted or deformed at all. So that is how CGC deals with these issues brought up by general relativity. Now, I'd like to sort of go off on a tangent now and take a look at some recent developments, some papers that were put up as preprints recently. And because they're dealing with what we're seeing from the Webb telescope, which has been an ongoing subject of the Torus report, I would just like to take a look at those very quickly. Again, I'll put links to these articles in the comments for the video. The first preprint I would like to take a quick look at is this one by Jung and his colleagues talking about these distant galaxies that Webb has observed. And he's asking, is it surprising in the context of standard galaxy formation models? And his answer is, and when I say his, I mean all of them, all of the authors. His answer is that, yes, it's very surprising. When they look at all of the various assumptions and processes and functions that cosmologists used to sort of predict how bright or how big these objects would be back at this time, he finds that that these things are more common or larger by a factor of 30 than what is predicted. Okay, now my complaint with cosmologists now, when they see this kind of thing, they are so far from being able to say that their theory is wrong that immediately they start striving, like they don't say, okay, our theory is just proven. Instead, they start talking about what they can tweak. And I'm sorry, but it's like arbitrary tweaking, right? Tweaking that doesn't make sense in terms of any physical mechanism at all. It's just arbitrary tweaking to make it work. So looking at all of this, in this paper, they propose, on the surface, it seems kind of reasonable. They look at, okay, well, what thing can we tweak that would get this result easiest? Okay, and so what they found is that if they could tweak the UV luminosity, meaning how much ultraviolet radiation was put out by these stars. Of course, by the time it gets to us, it's redshifted and it's infrared, but when it was emitted, it was ultraviolet. So if these stars suddenly emitted huge quantities of ultraviolet radiation, then that would explain how bright these galaxies are appearing. And yeah, that's true. Okay, well, but why would they be doing that? And in this paper, they make the case that they're population 3 stars. So what is a population 3 star? So stars are categorized by different things: their size, their metallicity, their brightness, how old they are, different kinds of things, their light output. There's different ways of classifying stars. And so a population 3 star is something that is theoretical, that it is based on assuming the Big Bang, right? You've got to assume the Big Bang to try to claim that there's massive populations, there's massive quantities of population 3 stars at the beginning. So what is a population 3 star? So the Big Bang posits that everything starts from this sort of primordial plasma of, protons, neutrons, and electrons all like jumbled together and not really forming any stars or metals or elements for that matter at the beginning. So at the beginning of the Big Bang, you don't even have any elements, right? It's all just this plasma soup of atomic parts. The word is escaping me now. Anyways, so it's this plasma, subatomic particles. So it takes a while for the first elements to form, which is hydrogen. And then it takes a while for that hydrogen to conglomerate together to form the first stars. So the very first stars ever formed would be purely hydrogen. Then it takes several generations of those stars burning out, going nova, and during nova, you start getting other elements form, which astronomers, cosmologists call all the other elements metals. We don't normally think of them as metals, but when they use the word metals in this context, they just mean anything beyond hydrogen and helium. Okay? So they're saying that at the very beginning there are these massive quantities of population 3 stars that were just hydrogen and there's nothing else there. And we only get the other metals, the other elements existing further down the road after we get generations of stars, forming, then going nova and so forth. Okay, and so I think that CGC or cyclic cosmology, that it would be possible in certain isolated places to get a star formed of purely hydrogen, but it would be like an isolated thing that's unusual and weird to see, and you would never in CGC ever have like huge quantities of population 3 stars. That would not exist. That is something that would only exist in the context of the Big Bang idea. So in this paper here, they're saying that we would get these huge UV luminosities. Fancy way of saying these galaxies would be hugely bright at this time, right? We'd get this huge luminosity, so they'd be extremely bright if they were population 3 stars, because population 3 stars are much more massive and they're purely hydrogen. And so you'd get a lot more output of light. And so that would explain what we're seeing. Okay, well, I'm sorry, but nobody's seen huge quantities of population 3 stars, okay? That's an assumption of Big Bang cosmology, right? You're not seeing that. But you're appealing to that to kind of rescue standard cosmology. And so it's kind of, to my view, sort of circular reasoning. And my point is that, in my opinion, all mainstream cosmologists and astrophysicists now, to me, they just seem on a mission to just insist, no matter what, they are going to appeal to something called efficiency, which is a fancy way of saying that everything in the early universe went into fast forward, right? Like efficiency means that galaxies were able to form stars and become more massive and take on these spiral shapes and do all of that much, much, much more quick than anyone ever expected. Okay? So instead of seeing that their Big Bang cosmology is disproven, they're just saying, oh, no. All that happened is everything right at the beginning happened, 10 times faster than we thought. Right? So how much faster about these efficiencies? Let's look at this next paper, which was really tremendous. It was great reading this. But, again, to me, it kind of falls down at the end. I mean, it's excellent work, most of it. So it's, and again, I'll link all these articles. So stress testing, LCDM, lambda cold dark matter, that's standard cosmology with these high redshift galaxies. What's going on? So these authors, they made a pretty simple observation here. Simple according to standard cosmology. So there are all of these models and functions and predictions about how matter managed to get separated into big clumps, and then those clumps form galaxies and all of that. And intrinsic and necessary to that are various descriptions and modeling of how dark matter was able to do that. Okay, because it is primarily through the mechanism of dark matter that standard cosmology comes up with ways of explaining how in the 13.8 or 13.6 billion years since the Big Bang, how all of that matter that was finely distributed, how did it get finely clumped and, you know, roughly homogeneous and spread all over the universe and formed into galaxies and all of that in that time period. And they need dark matter to do that. And so there's this correspondence between baryonic matter, and in this context, when cosmologists use the word baryonic, they just mean ordinary matter that we know and have experience with, right? So to a particle physicist, baryon is a specific type of particle, but for an astrophysicist, baryonic just means regular matter, all of it. It's not a specific type of particle. It's just all of regular matter. So anyways, the baryonic and dark matter has to move in tandem in certain strict proportions in order to form the galaxies that we see. Like every galaxy has its, quote unquote, halo of dark matter. And the baryonic normal matter, forms subject to the effects of that halo, that dark matter halo. So the authors of this paper are saying, with all these models of dark matter, there has to be correspondence between the dark matter and the visible matter. Okay, so they look at all of these galaxies that the Webb telescope is seeing from this perspective, from the perspective of the models of dark matter. And basically they're saying, from our models of dark matter, it is not possible that, if you do all the assumptions of LCDM, standard cosmology, it's not possible that we should see these monster galaxies, which are these blue stars here. And the only way it would be possible if the efficiency, and this epsilon here is standing for efficiency, and that it just means is how efficient the dark matter halo is at forming the baryonic matter into a visible galaxy, like how efficient it is. Okay? And so at efficiency of 1, right, this would be extremely unlikely, and that's at the highest efficiency possible, right? That we would see these kinds of monsters back then. And so they give another graph with the kind of the probabilities here. So with different efficiencies. So efficiency of 1 means that's the highest efficiency possible. In other words, the dark matter forms very quickly 100% of the baryonic matter into a galaxy, fairly quickly. That's an efficiency of 1. Now, what's the problem with that? Okay, what's the problem with that? The problem is, we've never seen efficiencies that high. When we look around, and I don't believe in dark matter to begin with, but making the assumptions of dark matter that standard cosmology makes, if we accept those assumptions and look at all of the galaxies that we see and try to rate the efficiency, you get efficiencies of like 10%, 30%. Nowhere ever do you see efficiencies like, greater than 60%. It just doesn't happen. Okay? And so once again, for cosmologists to say like, yeah, this is possible, and here's where I'm going to start arguing with the authors of the paper. I shouldn't argue with them because they kind of say that in the paper. They say that, these efficiencies are not realistic. So I'll give them credit for that. Okay? But looking at this graph here, these are the monster galaxies we're observing, right? And if you're outside the line, then that means it's impossible. Okay, so if you have an efficiency of like 30%, right, they're already outside the line, and 30% is like the most that we ever see, right? Efficiency. Usually it's somewhere between 10% and 30%. That's the efficiencies that we observe in the universe, right? And these galaxies are well outside of that. Okay, and so to me, it just is another thing, disproving standard cosmology. Of course, mainstream astrophysicists, they just simply say, oh, well, efficiency was near 1 at the early universe, obviously. It's like, well, okay, I mean, you say obviously only if you assume the Big Bang is correct. Well, yeah, if the Big Bang is correct and you're correct in saying, it's like 13.6 or 13.8 billion years ago, if that is correct, then the efficiency would have to be at 1. And even then, these galaxies are unusual, right? They would be possible with an efficiency at 1. But they'd be very unusual, and if you see a ton of them right at that efficiency, if Webb continues to see these monsters and sees more and more of them, it gets very doubtful the more of them you see, because it would be wildly unusual, unless you're going to insist that all galaxies formed with that efficiency back then. But I'm assuming they're going to see eventually stuff this massive even further back, and then they'll be really be in trouble. Okay, but at the end, after all the discussion, and a lot of this article is just excellent, and a lot of the discussion is excellent. The only kind of quibble I have is towards the end, when they're trying to kind of theorize, how might this be possible? Okay. How might this be possible? And so they start saying, if dark energy behaves maybe in different ways than what we're expecting in the early universe, then we might be able to explain all of this. Okay, well, to me, that's like out of the frying pan and it's out of the frying pan and into the fire, because I think that dark energy is every bit as much of a fantasy as dark matter. So if you're going to try and rescue the Big Bang, like, dark matter, it can't do it for you. And so then, okay, well, we're going to bring in dark energy and that'll do it. It's like, oh, okay, well, another made-up thing that we can't detect, and then that's how you're going to explain it. Well, anyways, I want to thank you for tuning in this week. Great having you here at the Taurus Report. And I think sometime, I don't think this coming episode, but I think the one after that, I think I'm going to try maybe doing some of these shows live, so that my viewers can participate. And be a little tougher on me, because if I do it live, then I've actually got to have a schedule, right? And then I got to stick to it, which I found that to be problematic for me, doing things according to a set schedule, but we'll see if I can swing it. Anyways, thank you very much for showing up this week, and we will see you again next week. Goodbye for now.